thank you so very much. And again, let me start by sharing my screen. Yeah, so up to now, I mean, we dealt with, or we focused on mathematics for deep learning. So we studied expressivity, optimization, generalization, explainability, and so on. And so now we come to, let's say, a bit different direction, which is deep learning for mathematics, meaning using deep learning techniques to solve particular problems which arise in the mathematical contents, like inverse problems and also partial differential equations. So this lecture will focus on inverse problems and how inverse problems can be solved by deep learning today in various ways. And we will particularly focus, I mean, inverse problems is a huge area. So here we will focus on imaging sciences, which is already a huge area itself due to different imaging modalities, like you see here, for instance, a CT scanner, and also then different tasks which you would like to solve. But let's start slowly and first, I mean, formally now introduce what an inverse problem is. I mean, in the previous talks, we already came across them sometime. Yeah, so for instance, I mean, the last talk, we also focused on a very specific setting, but here, let me give you a more general introduction now. So what is in general an inverse problem? I mean, we have some data, for instance, here, this meet, we apply some operator, and then the question is from the transformed version, can you get the initial data back? As you see here in this example, this is sometimes extremely difficult and seem even impossible. So some examples from imaging are, I mean, very classical. For instance, in painting, you have an image, you take out certain parts, and you would like to then recover the parts which were taken out and fill them in a natural way, whatever natural means. Or MRI, magnetic resonance imaging, where you apply in a coarse way a Fourier transform and sample it and then want to recover your initial data from that. Or also feature extraction, so you have an image and then you would like to extract certain features, for instance here curvilinear singularities and here point singularities. Now all those follow in the category of inverse problems. So in general, I mean, an inverse problem is, so you have two spaces, for instance, Banach spaces, or I mean, think of, for instance, L2R, L2Rn, and you have a map, an operator from one to the next, and you have an element of this space, and then you would like to compute x so that kx is equal to y. So that's the classical setting. That's solving an inverse problem, and we saw various versions in the finite dimensional setting so far. And usually you would like to be such a problem to be nice. And what nice means are these robustness conditions. So what you certainly would like ideally is that each time there exists an x which solves this equation, and ideally also this x is unique. And moreover, you would like to have stability so that if kxn converges to kx, that then also the original data converges to xn converges also. Yeah, so this would be nice, but as we all know, life is not that nice. So most of the times the problems are actually not well posed, but then what one says ill posed. Okay, so here are a couple of examples of such ill posed problems. So this is again the in painting problem. So we have our operator, let's say from KL201 squared to L201 squared. So always an image on a square. And then this operator does the following, it just takes out a certain part. And so this would be this operator, and now you want to invert it. So you want to make, to put it back on in the original, let's say, image domain. So you would like to fill the missing parts. That's obviously ill-posed, since you can fill these missing parts in numerous ways. So there is no unique G, so that Kf is equal to G. Sorry, there's no, so okay, I should say it this way. So if Kf is equal to G, then there's no unique F, so that Kf is equal to G. So there's no unique reconstruction. Magnetic resonance imaging is associated to an operator of this type. Already said, what happens is you have your original data, you compute the Fourier transform, and then you take point samples of it. Yeah? So here the original data, you compute a Fourier transform. This is this black and white picture in the background, and then you take samples. So you evaluate the Fourier transform at these red dots. And then from these values, you want to reconstruct your original image. Yeah? And now you can imagine, I mean, depending on how you choose this sampling set, if you choose it just in this low frequency regime, the reconstruction will be always blurry. If you choose it in an awkward other way, you will give strange artifacts in the reconstruction, and then you can also choose different sampling strategies and so on. Yeah, but still, I mean, this is again an ill-posed problem. And then another example is this feature extraction, where the operator K now takes the sum, and then I would like to invert it. So having an image, I would like to get the summand out. And again, this is, I mean, certainly highly ill-posed. You need to impose additional conditions on those two components so that at least you have an idea what you need to extract. Yeah, so these are some examples of ill-posed problems. So they all not satisfy these well-posed conditions, and that's basically true for most of the problems in imaging science, which makes things difficult but also exciting. So how do you tackle this problem? Well, you need to what's called regularize. So you need to impose additional conditions on your original solution. And how can you do that? Well, I mean, as I said, the goal is to bring in prior information, and also while doing this, I mean, ensure that everything depends continuously on the data, because if you go back, I mean, this is also sometimes the problem. Also, I mean, where to get this prior information from, how we incorporate it, we will see on the next slide, or one example on the next slide. And there are different approaches to take to do that. So there are approaches we'll see where you just take such a, what one says, regularizer from the shelf. You can handcraft it, and one can also learn it. So that brings us then also to deep learning. But first, I would like to briefly discuss those approaches, because then what we will do in the end is we will, well, I mean, we can use a neural network, but we also, which makes things, or which, let's say, which is a bit more advantage, we then combined with previous approaches. So this is also one big question in this field, how to combine then deep learning approaches with classical solvers, or with also domain knowledge. Okay, so there's a very standard approach to solve inverse problems. It's the standard, what says, Tikhonov regularization. Yeah, so the ingredients we already know. So this is my inverse problem. And what I now do is I minimize this functionally. And now you see the terms we already saw sometimes during the talk. So this term, if you minimize it and bring it down to 0, yeah, so then you would solve this problem exactly. And this is the term where you impose prior information, the so-called regularization term. This alpha balances between both. So depending on the value of alpha, I put, when I minimize this sum, either more emphasis on this term or more emphasis on this term. Okay, so that looks nice. So here we ensure that we solve our inverse problem so that we get an X with solvers, and here we ensure that we can incorporate additional problems. But then you can wonder, why is the norm a good way to define this regularization term? Do we really want to reconstruct the, let's say, image with the smallest norm? Why? No, I mean, that's not clear. And so one generalized this and to an arbitrary regularization term, and now you can put in different, let's say, components here. We will see a couple in a minute. So the regularization term, again, I mean, ensures that we get continuous dependence on the data and incorporate properties of the solution. Okay, so how to choose this this regularization term? I mean, there are various ways. We already saw, let's say, the norm, which is the easiest to just take, for instance, the R2 norm for this term. You can also take what's called the TV norm, which is also a rather classical approach. Sobolev norm might sometimes be a good choice. And the last is one can use sparsity of X. Yeah, so sparsity we also already saw several times during the lectures. And for instance, we also have representation systems like Weyfits or Scherlitz, which give us sparse representations. So therefore, this is typically also a very good choice. And if my vector X is sparse, meaning it has very few non-zero entries, then the L1 norm will promote that. Yeah? So then the L1 norm will be small. So why is the L1 norm such a good norm for testing whether a vector is sparse or not, meaning it has very few non-zero entries? Well, I mean, just look at this example. If you have here a lot of different, let's say, elements, if I would now minimize the L2 norm, the minimal L2 norm on this line is this point here, because you can take an L2 wall, blow it up, it will hit this line somewhere, but the minimal L1 norm is this point. So because the L1 norm is differently shaped, and it will hit this line at a point where you have a vector which has one non-zero but also one zero component. No? So in that sense, I mean, the L1 norm promotes sparsity, and it's a very classical choice. And that brings us to what's called sparse regularization. Now, sparse regularization, as said, is based on the fact that typically signals are sparse, meaning they have very few non-zero components. And for instance, in R2, in R3, if you look at those vectors which are too sparse, you get a picture like this. So this is certainly not a subspace, it's just a set of k-sparse vectors. You can also, if sparsity is too restrictive for you, people often relax it to what's called compressibility. So then instead of having, if you sort your coefficients in your vector in this way, at some point just having zero entries, you get some power law decay. Okay, so that is sparsity, and it's today kind of considered a paradigm that you can to some extent always achieve sparsity. Either the data is already sparse itself, or you can make it sparse. And so this we also already discussed at some point, the Weyfits transform, which is one way to achieve sparsity. And so here, this was a Weyfits system. And here you see some pictures of elements of a Weyfits system. And if you now compute this Weyfits transform, you get an image like this. And again, this JPEG 2000 compression standard is based on this, because then all these areas which are black, you can just take out and just store the ones which are white, and then reconstruct and still get a very good reconstruction. Now, so remember, we also compared the explainability method to compression with, for instance, a Weyfits system. And so it's today, yeah, to some extent assumed that no matter which data you have, you can always find such a sparsifying system. There are actually also learning algorithms for doing so. Also have some data, and then you can learn a representation system which gives you such properties. Now, we also already introduced Scherlitz as a sparsifying system for a particular class of functions for these. Yeah, so if you remember, these cartoon-like functions, which look like, I mean, a simple version of an image to some extent, I mean, with a very distinctive discontinuity curve. And what we discussed can be, I mean, in very rough terms, we summarized also that Scherlitz fulfill an optimal compression rate for those cartoon-like functions. And again, I mean, these algorithms, if you want to try things out, you can find there. Okay, so for data, I mean, usually you can find such a sparsifying system. So now you want to use it for regularization. And the way you can do that is, if you look here, this was before this arbitrary regularization term. Now we fill it with life. And again, we put here the little R1 norm because that promotes sparsity. You see here again the image, which shows that the L1 norm pushes the solutions towards the axis, which is where the sparse vectors are, with very few non-zero entries. And so then, since F might not be sparse itself, you take the inner product with a suitable representation system like wavelets or shearlets. And so this is what you then impose. So you assume that your original image is sparse in wavelets or shearlets. That's the condition you use for regularization. And then you solve this minimization problem. Okay, so that is sparse regularization. It's a very classical technique and can be widely applied to different types of inverse problems. And so, for instance, if you think about this image, which I showed you, where you take out certain parts, then if you now will put this, let's say, prior information in, then you will see that you can actually, in a very natural way, fill in the missing parts. Okay, so that's sparse regularization with this specific regularization term. Now, with all these classical approaches, there are certainly also problems. They reach their, let's say, boundary, certainly to some extent at some point. And let me show you one example, which will then also be our running example later on. So we already discussed magnetic resonance imaging. Here we see another method of medical imaging, which is computed tomography. So computed tomography does something a bit different than MRI. And what it does, it computes the so-called radon transform. But let's first take a look at this image here, what happens. So, I mean, most of you, I guess, are very young, so I've never experienced lying in a CT scanner. But what it is, I mean, it's this tube around you. I mean, there's also some rotation happening, and then it takes images, which then from the measurements, I mean, the radiologists also need to reconstruct. So let's say this is the interior of the human body. What happens is line integrals are computed. And then you get here one slice of the sinogram. And then the device is rotated, and each time you get here line integrals, and each time a new slice of the sinogram. And then it is rotated by 180 degrees, and that way this so-called sinogram is filled. These are then the measurements, and the task is from these measurements to reconstruct the interior of the human body. So that's the basic problem which one faces, and you see here the precise definition. So you have here your f, which is this function, and then you compute line integrals at different angles and different offsets, and that way you acquire this RF, and that is RF, the sinogram for which you want to reconstruct the interior. Now things become really hard if you cannot do this 180-degree rotation. That is, for instance, the case. We already discussed briefly electron tomography at some point. So now you see here a tiny piece of it. So the probe is sitting in a device, and you see now if you turn this device, at some point the rays cannot get through anymore. So the angle where you can rotate it is limited, and you cannot do the full 180-degree rotation. So in that sense, it is only sampled in a restricted area, meaning there's a whole chunk missing here from the sinogram. So it's different from low dose, because in low dose, you, for instance, just sample each second angle, which is much easier than if you have a whole entire, let's say, area missing. And so you see here, I mean, the problem classical approaches fail. Classical approaches face. So here you see the original image, which we typically would like to reconstruct. and then the measurements are taken with a 60-degree missing angle. Yeah, and so here you see a very traditional reconstruction, and it looks, I mean, really bad. You see a lot of distortions here and here. And then if you use this sparse regularization approach using shearlets, which we discussed, yeah, so this term, this additional term, this regularization term is the little n1 norm of the shearlet coefficients. Then you get a better reconstruction, but still you see, I mean, if you look also at the zoom up here, you see, I mean, structures are not really accurately recovered. Yeah, and here, I mean, you have a lot of blurry parts. Okay, so this problem we faced, and now certainly the question is, because it's also a lecture series about deep learning, what can we do with deep learning techniques? So, and again, as I said, I mean, a main question in the area is also to which extent to use deep learning, and to which extent to also incorporate knowledge, for instance, about the physics of the problem, like this forward operator and so on. And so this also depends very much on the different applications. Okay. So in general, I mean, as I said, there are these classical approaches, which actually, I mean, also have the advantage that we have a lot of theory for that. And right now, I mean, the deep learning approaches, as we discussed also during the last days, well, I mean, they have robustness issues. We cannot exactly predict what they really compute and what is trained, and so on. So that is also another reason one might want to restrict the use of deep learning, in particular sensitive applications, and only use it where it's really necessary. So the first type of approaches of these hybrid approaches, and again with hybrid, I mean model-based, so classical approaches like we saw just during the last minutes, and deep learning, so a hybrid approach between both worlds. The first type I might call supervised approaches. The easiest you can do is you train a neural network end to end. Yeah, so you have your inverse problem, k f is equal to g, and what you want from g to recover f. So you train a network with a lot of g's and a lot of f's to do that. So you completely ignore that you might have knowledge of k, of the forward operator, and so on. So this is in a way the most, how to say, pure approach, pure deep learning approach, what you can do. So then, since you actually have additional knowledge, for instance, you know how the measurements were taken typically, I mean, if you have a physical device, then you can try to incorporate that information somehow in the neural network or in the overall algorithm. Yeah, which is usually a good idea because, I mean, if you have knowledge, I mean, why ignore it? On the other hand, makes things maybe a bit more complicated. The end-to-end approach is certainly, I mean, the easiest you can do. You have your data, you just train your network, that's it. Then what one can also do is to combine neural networks in a certain way with these classical solvers, to insert it in certain parts, use, let's say, this overall strategy of reconstruction, and use neural networks only at certain parts where, for instance, the denoising happens, something of that type. So there are plug and play strategies, which we will also see in a moment. Yeah, so these are supervised approaches. So the network is always trained with the full data to some extent, but still the idea is to combine it in a best possible way with classical approaches. Only here, this is, let's say, an only deep learning approach. Then there are approaches which I might call semi-supervised. So for instance, I mean, there are approaches where we saw, I mean, the regularization term should encode prior knowledge, where the regularization term is chosen as a neural network. Yeah, so then, I mean, the neural network doesn't need to learn, let's say, the full problem. It only, as it says, requires a set of labels to check how hard this inverse problem actually is. Yeah, so in that sense, I mean, it's, yeah, so in that sense, I might call it semi-supervised. Yeah, so it's only used as a regularizer, not, I mean, for the let's say, for the full problem. Yeah, and so there are various approaches. So we also see an example of these approaches. And then unsupervised approaches, so for instance, of that type are is one approach which is very interesting and which we also discuss in the end, a deep image prior, where you parameterize the solution as the output of a neural network, and there you actually in a certain sense don't even train the neural network. So there, I mean, the neural network is used in its purest form to some extent. I mean, it doesn't require training, you just randomize things. And in that sense, it's, one might call it unsupervised. So there are no labels which you use here. Okay, so these are, in a certain sense, three different directions in this whole area. And I would like to now show you some examples for each of those. And let me also mention that, again, I mean, since we are now in the area of imaging sciences, we will use convolutional neural networks, since, as I also said, to a certain extent, I mean, in particular, if you classification or in general, I mean, the convolution operator seems to be appropriate because, I mean, it doesn't really, for instance, for classification matter where certain objects are in the image. And so the way this network is built up is that in each layer we have a convolution, activation, pooling, and an output, and then these are stacked. Okay, supervised approaches. Now, I mean, the easiest you can do is, as I already said, training a network end to end. That I won't discuss here again. I mean, so this is an approach which is maybe a bit more, how to say, a bit more sophisticated than just this end-to-end approach. People call it typical denoising direct inversion. But it's also an ad hoc approach to some extent, but it started interesting research direction there. And so the idea here is quite simple. Yeah, so the first reconstruct. So this is my sinogram. This is a traditional reconstruction, so-called filtered back projection. And then, since then you have some artifacts in here, you use a neural network to remove the noise, to improve the image. Yeah, so here the neural network is used for denoising in a certain sense. Yeah, and so the neural network here, I mean, doesn't need to learn the physics of the problem or anything. It basically just needs to learn denoising, and maybe it needs to learn structured noise. Yeah, because, I mean, out of this reconstruction, the noise might have a very special form. Yeah, but basically the neural network is used for denoising tasks. So you invert and then you denoise. So it's a very, very simple approach, but also to a certain extent effective. Good. So this is just putting one thing after the other. First classical approach, and then a deep neural network.
Excuse me, is it supervised or unsupervised?
So these I would call supervised to some extent, but I mean, so the labeling, yeah. So I mean, this I would how to say, I would put it in that category, but I mean, this is up for today. Okay, so let me also mention at this point, I mean, that typically, and we also already discussed this for inverse problems, we take so-called UNet. So this is the traditional neural network which is used. And there are actually, unfortunately, very few results which study this particular architecture. And that's also something which we'll discuss tomorrow, that there are a lot of architectures which are not really that much the focus of mathematics, of deep learning, but which should be. Now here, this UNet, you see, I mean, let's go in a bit more detail how it's structured. It's this convolutional neural network, and you see, yeah, so you start here with the image size, then you go through the neural network. So first you compress basically until you end up here, and then again you expand, since the outcome of such an inverse problem needs to be also an image of the same size. And so since through this compression stage, you might lose some information, you have also some skip connections in between. So these are called skip connections, which now don't go to, let's say, the next layer, but to, layers which are very far already ahead. And so these can then be used during the training process to also bring information from this side to this side. And intuitively, why things work with a unit seems to be also that in this area here, key information is extracted through this compression, which seems to be, a good way to handle things. But there are some theoretical results in this direction. I think it's also something which should be studied much more. Okay, in any case, so this is usually if you have to solve an inverse problem, particularly in imaging, use a unit, because most of the approaches are based on this particular architecture. So it's sometimes also called like a so-called autoencoder with some skip connections in between. Okay, so then, another, let's say, approach, which is maybe a bit more sophisticated, is this plug and play. So what is plug and play now? We saw, for instance, sparse regularization, or we saw Tikhonov regularization as a particular solver. And if you look at the solver itself, at the algorithm, then you realize, it's typically an iterative solver, which you use to solve such an inverse problem in the traditional way. And these iterative solvers typically consist of different steps. And one step is often a denoising step. Now, neural networks are really good at denoising. So therefore, the idea with this plug and play is basically to take a trained neural network and insert it there. And so basically to train it for doing denoising in that sense. And so this is typically a plug and play because you can plug things in at different places. You can make it also a bit more sophisticated, still based on traditional solvers, where you then replace basically different other steps by neural networks. Yeah, so this is, as I said, a different philosophy. So you take the traditional solvers, but you replace parts by a neural network in a certain manner. And so, due to the question which were just raised, you can also wonder whether to some extent these types now belong to semi-supervised or supervised. This is up for discussion. I would put them here because they are in basically the entire solver, unconnected, contained, and also to some extent need to be trained with the corresponding labels. Okay. So I would now like to show you also one approach which combines deep learning and traditional solvers, these sparse regularization solvers, in a bit different manner. The philosophy here is, which I already said in the beginning. So now, for the previous approaches, if you look at those, you use basically let's say it that way. The neural network basically touches everything. And if there's a problem, for instance, a robustness problem, this will affect the entire reconstruction. But it might be better to just surgically use deep learning only where it's really necessary. And so you can do that in various manners. I would like to show you one particular approach here. And so the idea now is to use classical model-based methods so far as they are reliable, and then only use deep learning exactly where it's necessary and where you don't have anyhow enough other information. And so the key idea of this approach, which I would like to show you, is that, and that is often a guiding principle. Edges are usually the key part of images. And you saw that also when we defined shearlets, because we defined them depending on these cartoon-like images, and there we also said cartoon-like images are defined that way because edges are the key parts of images. And so here, not only edges are typically the key part, but even more what is called the wavefront set, but these are just edges with their direction. And so this gives us a lot of information. And so this is what we will primarily look at also then for the reconstruction. So the shielded transform is something which can achieve that. So let's look again at this, the computed tomography problem, the limited angle one, where we don't have access to the full sinogram. So what you see here is that you don't see anything. I mean, so this is the reconstruction from a sinogram where you only have data between -15 and 15 degrees. You reconstruct with a very traditional method and you see that you don't see anything. If I now increase the angle, you see that suddenly, I mean, things appear. But there's something different, which is also very striking. Yeah, so observe what happens here. So at a very early stage, you get already very clear picture here of these edges in that direction. And so then, and then things become more clearer in these areas, and so on and so on. But apparently, I mean, depending on the directionality of these edges, they can already be recovered at a very early stage. And so this is something kind of striking, which we can actually use. Okay, so what seems to happen is that some of these edges, like here, are already visible at an early stage, and others are not visible. And now, I mean, think of what actually the CT scanner does. It samples along lines. Now, if these lines are only in this direction, I mean, these things will be definitely smeared out. I mean, there's no way you can precisely recover those at this point. However, these curves will already be visible at an early stage due to their directionality. Because here, if you scan at one point, you still have something positive, and then you will have something zero. So therefore, you can already see these edges because they have this direction, depending on which angle you measure. And you can make this mathematically very precise. Okay, so yeah, so you can phrase this, as I said, in terms of this wavefront set. So what is a wavefront set? Without going into the technical details, the intuition is these are points on the discontinuity curve on the singularity each time with their direction. So this wavefront set is a point on the curve with its direction. And so you can show this in such a diagram, in such a phase space, where here you have the plane, here you have the direction, and so each point now of this curve is mapped to one particular direction. So this would be mapped to the direction, to this direction, which is here, and so on. Yeah, so this would be the so-called wavefront set of this object. And now what happens, what we saw in the previous slide, I mean, depending on the angle, certain edges and the direction, you can already recover early, but some you can't. So the problem you can phrase in terms of you have some missing parts here in the wavefront set. And this is the problem for also the classical method, because these gaps might be too large to actually recover them. But what one can use is that Schild can identify the wavefront sets, and also they are able, due to their structure in Fourier domain, to separate the visible and invisible part. So what one can do is the following. So this algorithm we call it learning or learn the invisible. So first, so it follows exactly the philosophy I told you. First, we solve the classical problem. So this is sparse regularization. You see here the operator, the radon transform. These were the measurements which we have. We minimize over F. Here you see the regularizer, the sparse regularizer with the L1 norm, and here the shielded transform. So the inner products of my shieldeds with F. The weight here, I mean, don't get confused about that. The reason there's a weight is that so this is a multi-scale transform, and so it's sometimes good to also weight the different scales, but I mean, maybe ignore that now. Okay, so that's the traditional solver. We get a reconstruction F star, which, as we know, is not that great. So this we already saw. You have some blurry areas here and here. But you get this solution, and now you cannot get much further with classical methods, so you need to use a neural network, but we only want to use it where it's really necessary. So it doesn't make sense to now apply a neural network to the entire image, because parts, I mean, are already very well recovered. And to really analyze which parts are recovered, what we do for that is we apply another shielded transform to this F star. And what we observe is that some of these coefficients, so these are, again, I mean, inner products between my F star and shielded elements, which are indexed by these JK. So for some indices, these inner products are almost zero, and for others, which are maybe the visible ones, this is reliable and nearly perfect. So these we don't touch because these are already perfect, so it doesn't make any sense to apply a neural network again to it, because it might make things worse. It might distort things due to, for instance, also the non-robustness of neural networks. And also it gives us a chance to just use a neural network on a much smaller set. So these we need to learn. And now we train a neural network for doing that. So from these reliable ones to learn the invisible ones. So and we train it on the ground truth. So that way we also can fill these coefficients correctly with this F. Then we need to go back to the image domain, and that gives us the reconstruction. Now, okay, so let me show you some numerical experiments for that. What we will see is, so this is real data. We have a 60-degree missing wedge, and then we will in a second step, use this neural network, which was trained on this type of data, so on real patients, for a very different task. And so the question is, does it generalize that way? Okay, so this is the ground truth image. This is crude reconstruction. Remember, we have the 60-degree missing angle, filtered back projection. You see here the relative error. And you see here another measure, which is much closer to the human visual system. So which measures much better how we humans perceive an image. Okay. Anyhow, so this is one TV. Then this is reconstruction, sparse regularization with shearlets. So this image we already saw. We saw also the problems which occur here and here. So now, this image is an image where the network was trained to a certain extent end-to-end, so on the entire image. And you see things get better, but it's not perfect. But then if you combine, let's say, both worlds in the way we just discussed in the algorithm, this is what you get. And you see it's a huge difference from this to, for instance, this reconstruction with classical methods. And so, I mean, if you like metrics, you can compare them as well. And then you see that, for instance, I mean, so this method is actually the best in each of these metrics. So that's relative error, the so-called PSNR, and these two are measures which are much more adapted to humans, to the human perception. And so here, this is a measure which we developed on our own, where you can also download the code. It's something which performs better than the self-similarity index and also can be computed much more efficiently. Okay, so now let's see how things work on very different type of data. So this is data from a lotus root. So colleagues there from Helsinki slice the lotus root and put some metal things in and put this in a CT scanner. Again, the ground truth. You filtered back projection, so the network has never seen images of that type. It's got trained on the other type of images. So this is the classical reconstruction, again, classical. And also this is the classical reconstruction, sparse regularization with shearlets. This is using a network on the entire image. And then this is the approach where you combine the classical approach with deep learning in the particular way we discussed. Okay, so let's go to a different type of approaches, which one might refer to as semi-supervised approaches. And here I want to show you one approach, which is called adversarial regularizers, by Ludwig-Maximilians-Universität and Carola Schönlieb. So that's a nice idea. So here you see the approach. The idea is to use a neural network in a particular way as a regularizer, and then the network is trained like, so we saw such an image already before when we discussed a GAN, a generative adversarial network. So now the regularizer is trained, with a certain similar philosophy to discriminate between the distribution of the ground truth images and the distribution of unregularized reconstructions. Remember, GANs were typically trained to be able to distinguish or discriminate between real images, here for instance training set, and fake images. Sorry, they were actually trained to then be able to generate images which are not distinguishable from the data manifold. So here the regularizer is trained to discriminate between those two, and therefore we can use it for regularization, because as we said, here we need to impose conditions on the original image. And so what we want is that we promote here the distribution of the ground truth images. So that's the philosophy. Let me just also from that paper show you this figure where you see here some numerical results, and here you see also again some numbers, the PSNR and the self-similarity index we already saw before. And here you see the adversarial regularizer, which comes extremely close to a fully supervised neural network. So that's actually a really nice result, and it shows in some sense that also this is a very interesting direction to substitute then the regularizer itself directly by a neural network in various ways. So here the neural network is basically not, only half trained to some extent. It's not trained with the full labels of the data. Okay. And the last, what I would like to show you is what's called deep image prior. It follows now again a different philosophy. So here the idea is that again we want to use a network in some sense as a prior, but here we use just the network which is randomly initialized, and for a certain reason this seemed to work extremely well, which is actually quite surprising. So here the network is not trained, but this network, which we see in a moment, this generator network, seemed to already, when it's randomly initialized, seem to already capture some image statistics. And so you see here some results of their paper, and what you see is the ground truth. And so this is here this approach, deep prior, which is not trained, which gets very close to the ground truth. So they use a deep generator network, which is a normal neural network, so a parameterized function, which maps now a random code vector Z, which we put in here, to an image. So it generates images. So the output is an image. The random code vector doesn't necessarily need to be an image. And so in that sense, we interpret it now new, so we use it as a generator for images where the neural network can be then viewed as a parameterization of this image, namely a parameterization of the image by these parameters of the neural network. So in that way, it generates images, and the image is to a certain extent parameterized by these parameters, which are though not learned. And in a certain sense, intuitively the architecture which is used, so they use units, seem to already incorporate some statistics of natural images, maybe because here's the multi-scale structure. But what then they solve is exactly what I said. So this is a traditional way. And so they consider this minimization problem. So you see here again, you have Y, which are your measurements. And now you use this generator, deep generator network to generate images, so generate axes, and then you minimize here over the parameters. And so then, I mean, once you have solved this minimization problem, you have gotten a theta star, then this way you can also produce this X star, which is then the image which you get for reconstruction. And so this figure from the paper shows, I mean, if you look at this arrow here, and now you take different types of images. You take a, let's say, denoised image, so a clean image, an image with a bit of noise, and then, as it says here, an image shuffled, and then completely random noise. And now you minimize this. It seems so that the generator network, which tries to generate now images so that this is matched and this is brought to 0. If it's a real image, it seems to be much more willing, let's say, to get quick convergence than if the image is of that type. So in a certain sense, I mean, the architecture seems to sense what a good natural image is. Now, I mean, in each case, I mean, this can be brought down to 0, but if one has, let's say, a clean image, it seems to be much quicker. And so these are some figures also from the paper, what you here observe. This is the original image. And then with this deep prior approach, you see that you get, I mean, very good reconstruction, which is basically at the level of fully trained neural networks. Now, which is actually very, very surprising and also worth taking a look at from a mathematical standpoint. Okay, so let me conclude. So in inverse problems, we first looked at a model-based side, and we saw and discussed a particular way to solve inverse problems, namely by sparse regularization techniques. So that assumes that the original image has a sparse representation, and then imposes this as a prior. And we then explicitly took a look at cheerlets, which can to a certain extent be proven to be optimal for imaging problems, and use that for getting a sparse expansion. So then we use sparse regularization with cheerlets, but then we saw that in certain problems where we have a huge chunk of missing data, of missing measurements, so where we have something which is tremendously ill-posed there, these classical methods sometimes reach a barrier. Then, I mean, deep learning came into play, and there are numerous ways to either use deep learning out of the box or to combine it with model-based methods. So you can train a neural network end-to-end. That's basically the easiest. You need a lot of data for that, which is sometimes something people are reluctant because they don't have that much data, and then you need to do or go a hybrid route anyhow. But in any case, so if you train a neural network end-to-end, you basically forget everything about the problem and just look at the data. It is often smarter to use additional knowledge, like about the operator, maybe even combine it with classical solvers in a suitable manner. Maybe follow this philosophy, which I advocated, to use classical solvers as far as they are reliable, and then combine that with neural networks. Then there are other approaches which one could call semi-supervised, where, for instance, one uses a neural network for the regularization of a neural network, where one uses a neural network for regularization of the inverse problem. These gave also very good results, as we saw, and then maybe a different category where we characterize the solution as the output of a neural network. So we use a deep generator network to produce our images, and then use this to a certain extent as, I mean, one shouldn't say a prior, but I mean, what one sees and what we discuss is that going that route using these generator networks, one can get very good recovery results, although this network is actually not trained at all. And with this, I'd like to conclude, and thanks a lot for your attention.
Gitta, are there any questions? I'll ask the live audience first. Yeah, go ahead. No, I need to, yeah.
Thank you very much for the interesting talk. I was just wondering about the last approach, the unsupervised approach of deep image prior. Although they don't train the network, they still parameterize the solution by a certain architecture. And this architecture determines the regularity of the function that can be realized that way. So in some sense, it is a sort of a prior in the sense that you specify more regular space in which you're looking for solutions. Is that the right intuition?
Yeah, so you can see it that way. Yeah, and as I said, I mean, the architecture is of a particular, let's say, of particular importance there. And apparently, I mean, this architecture seems to, as you rightly said, seems to give, let's say, the right type of regularity for the solution. Yes.
Thank you.
Other questions? If not, maybe we could look at the questions on the chat. I can manage that.
Yeah, so there's one question about explainability methods. So if you try to apply explainability methods to the shielded regularization method for the reconstruction, limited angle tomography is severely ill-posed, so I would be curious to understand what exactly the neural network reconstructs. So now these explainability methods are, so which I showed you, are tuned towards classification or regression. So here now, if you have, so for instance, I mean, if you would use this reconstruction and then would use, let's say, a classifier afterwards, I mean, then you could directly apply it, because then, I mean, you could go back, let's say, both stages. But here, yeah, I mean, this type of approach, I wouldn't know how to, I mean, one need to think about how to use this type of explainability approach. I mean, for this, for reconstruction of images, there are other approaches which put also like a heat map on the reconstruction, but then it is more the idea of her certain reconstruction in certain areas. Yes. So there is, for instance, also interesting work by Oza and Öktem in that direction.
If I could ask, perhaps you could say a few words about how you could reconcile these methods with the result that you told us in the previous lecture about, you know, even the sparse regularization optimization problem is not computable.
Yeah, what should I say? I mean, so you see these results. I mean, as you saw, I mean, we don't also have any error bounds right now, but still, I mean, in light of the results I told you about yesterday, about in the morning, yeah, one has to say, even if you have, let's say, error bounds, and now if you would compute it on a digital platform, I mean, these error bounds would not hold. So this is the problem which you face there.
Well, no more questions. Please join me in thanking Gitta again for a wonderful talk.